Okay, hello everyone. So we are starting a new topic, conservation of energy. So you already have an idea what energy is. Energy is ability to do work. And the previous discussions, we briefly mentioned one type of energy. Now there's many different types of energies that we discuss in physics. Kinetic energy, it is the energy due to the motion of an object. If something is moving, we say that it has kinetic energy, moving energy. Another type is potential energy. We will go into details in a little bit, but potential energy is due to the location, like how high above the ground an object is. The further high you go away from the earth, more potential energy you get. So it comes due to the height or the location of the object. And also there's another type of potential energy due to the shape or the change of shape of the object. Like if you make a change to the shape, if you stretch something like a spring, or if you compress something, it gains some kind of potential energy. There's energy comes from nuclear reactions. So it's energy of small particles that during these reactions, nuclear reactions, they release this energy. So that is another type. There's heat energy, one of the basic energies. So there's different ways that we can talk about energy, but here we're going to limit our discussion to mechanical energies. So this kinetic and potential energy together are called mechanical energy. There's nuclear energy, there's chemical energy, there's heat energy, one of the most fundamentals of everything. So we're going to talk about these, and then the concept of energy conservation. Energy can transform from one type to another, can change the form. Kinetic can become potential, potential can become kinetic. These energies can become heat energy at the end. So when energy is changing to a different form, how the numbers are changing, is it going to remain the same, the total number? So those are the things we're going to discuss under energy conservation. And then finally the term power, which is also closely related to energy, so we'll talk about that. Okay, all right, so let's start with kinetic energy. So we are supposed to discuss this topic in class, so therefore I'm not planning to spend much time on this. This is the energy due to motion. If something is moving, if an object is moving, let's say a car moving with some velocity v, it could be a person running with some velocity, it could be a small molecule like a carbon dioxide molecule moving through the space. Anything that has mass and a velocity, any mass that moves acquires this energy called kinetic energy. So if we say the mass of the object, for an example, for this car, let's say the mass is m, velocity is v, kinetic energy is given by half times mv squared. So if you put some numbers into this, it's pretty simple. Let's say the mass of the car is 1000 kilograms and it's going at a velocity of let's say 20 meters per second. Kinetic energy of this car right now is half times 1000 times 20 squared. So what's the answer? Half times 1000 times 20 times 20. So half 1000 20 20 is 10, so 200. This many 200,000 joules, right? So this is how you calculate kinetic energy. Is half times mass times velocity squared, and the units in joules. It's an energy, so we keep units as joules. Another simple example, let's say all the examples gonna be the same. Person 50 kilograms running at a speed of 6 meters per second. Kinetic energy is half times mass times velocity squared. Let me say he's running at 5 meters per second. Easy to work with, so 5 squared. We have half times 50 times 25 times 25 625, I think, joules. Okay, so kinetic energy depends on the mass. Bigger the mass, more kinetic energy. Depends on the velocity. Bigger the velocity, more kinetic energy. All right, so okay, so we'll move on to the next type. This is how you find kinetic energy. It's one type of mechanical energies. Okay, so let me erase the whole thing. Potential energy. Potential energy is another type of mechanical energy. We say that an object can have energy by virtue of its surroundings or due to where it is. So we divide this into two types: gravitational potential energy and elastic potential energy. Gravitational is due to location. So let's say this is the surface of Earth, and you have an object, some mass, sitting on the Earth's surface. Now we know that this object has a weight mg. Now you want to raise this to a height h. You want to put it up here. The weight is still mg. Now you raised it to a height of h. Now to lift this object, you have to apply a force at least equal to the weight of the object. So the force you have to apply is also mg. Now by applying this force mg, you're going to lift it to a height h. So what is the work you do? Work needed is force multiplied by distance. You need a force of mg at least equal to the weight of the object. multiply by the distance or the displacement, the amount of meters it moved, which is h in this case. So the work you did equals to mgh. Now the object is up here. You spend mgh amount of joules. We say that because it's so many meters above the ground, it gains potential energy. It has the ability to do work because of its new location, and that potential energy is given by mgh. So potential energy is mass times gravity times height. So when you lift something above the Earth's surface, because gravity is pulling down on it, the object has the ability to do work. It can fall back on Earth and, hit the ground, do some damage, some kind of work, right? It has that ability when it is up there. So the further up you go, more potential energy you gain. And this is called gravitational potential energy. It's due to the location, due to how far it is from the Earth's surface. Okay. It's also measured in joules. We can do a simple quick example. Let's say this is a 50 kg box and you raise it to a height of 10 meters. What's the potential energy? mgh 50, 9.81, 10 meters. So we have 500 times 9.81, 4905 joules. Now the idea of potential energy is if you release it from this side, if you just let it go, it's going to come down. And you see, while it's falling, it's going to be a free fall. It's going to gain speed. It's gaining kinetic energy. So by the time it reached back all the way back to the ground, all that potential energy it had up here, this is potential energy, will become kinetic energy down here. At this point, at the ground level, the object is moving at the highest speed. It has the highest kinetic energy. Later we will learn that all that potential energy it had up here, most of it has converted into kinetic energy, giving the speed. Okay, so that is, we normally call it potential energy, but the better word is gravitational potential energy. Okay, so that is all gravitational potential energy. Now let's talk about this elastic potential energy. Due to the changes in shape, you can purposely you take an object and you can purposely make changes to the shape. You can compress it, you can stretch it, you can squeeze it, you can make some deformation. And most of the objects, many things we see around us, they try to go back to their original shape. Think about the lab ruler, right? Those wooden rulers. If you bend it a little bit, it wants to come back to its original shape, right? If you take a spring and stretch it, it wants to go back. If you compress a spring, it wants to expand again to original shape. Up to a certain limit, like take a ruler and if you bend it too much, it's going to break. That is, you are going beyond its elastic limits. Think about a volleyball or a soccer ball. You try to squeeze it by applying force with your palms. It's gonna press against your hands and try to come back to its original shape. The moment you remove the force, things will try to get back to original shape. Not all the time. Things like things like clay and all that, wouldn't show that much of elastic properties. You can stretch them, they won't come back. So that is elastic potential energy. So we're gonna talk about springs under this. This familiar little piece of metal where you can compress it, can stretch them, and because of the elasticity, because of this elastic potential energy, you can do work. They can store energy, like the projectile launcher is a good example, right? You squeeze the spring and then it gains that potential energy to shoot the plastic ball outwards, giving it kinetic energy. Okay, all right, so let's look into some details of potential energy. Okay, so let me clear the screen one more time. Okay, so potential energy. Potential energy is due to height differences. So here's an object with mass m. You raise it and put it up here, maybe top of a building. This object has potential energy. Now if the mass m and if the height is from the surface is h, potential energy up here is mgh, mass times gravity times height. Now to calculate the potential energy of something, we need to know what the mass is. We need to know the gravity, which is 9.81. So mass in kilograms, this is gravity, and the height. To measure the height, this is the final location up here. So let's say final, this was the initial location, and then you take the difference from initial to final. We always define a zero potential energy level like a reference point. Now up here it has mgh, we say relative to ground or relative to the 0 point. So this level where you make all the measurements from is called the zero potential energy level, right? All your measurements are done from the zero potential energy level. Now the standard is we take the surface of Earth as the zero potential energy level, but based on the problem, like when let's say we are in the classroom, we can take the classroom floor as the zero level and then make measurements from there. Let's say you are setting up some experiment and everything is on the table, your lab table, and then you bring things up from the table, you're increasing the height from the table. You can take the table surface as your zero potential energy level. It's all about where you want to define as the zero level, right? It's not necessary that it has to be the Earth's surface all the time. It's up to you. You can take the entire experiment, instead of the second floor, you can go to third floor and do it. So you can define third floor as the zero potential energy level. So it changes. You just have to know what is your zero level. Sometimes you need to identify what is your zero level. Okay, so as I said, a simple math problem one more time. If this has a mass of 10 kg and you raise it to a height of 2 meters, how much potential energy it gains at this height over here? mgh, which is 10 times 9.81 times 2, so what, 220 times, something like 198, something like that. Let's see what the actual number is. 196.2 joules. Okay, so the potential energy of the object over here, up here, is 196. If you come to the midpoint, if you bring it down by 1 meter, it will be 10 times 9.8 times 1, so that will be half of that, 98 joules. Right? If you bring it all the way back to ground, you're going to lose all that potential energy. Potential energy becomes 0 because you are at the 0 energy level. Okay? So this is how you do math with potential energy. So we talk about gravitational potential energy. This example I gave you is gravitational potential energy. Now let's talk about the other type, elastic potential energy. A simple example is a spring. So here we have a solid surface, here we have a spring attached, and let's say you're going to apply a force and stretch the spring by x distance. Now elastic potential energy, there is no single formula for everything. Gravitational potential energy, we have one, mgh, but elastic potential energy based on what kind of object we are dealing with. Now here it's a spring. Now you can stretch the spring by a distance of x by applying a force F. You should remember that we talk about the spring constant. The force needed to stretch it by a distance x is given by kx with a negative sign in the front. The work you do, this is a changing force. It starts from 0 and increasing. So again, in one of the previous lectures we talk about this, how to find the work. Work is given by half kx squared. This is same as the elastic potential energy. So for a spring, this is only for a spring or spring-like object, things that behave like springs. Linear objects where you can stretch them or compress them. Elastic potential energy can be given by half times kx squared and is measured in joules. Okay? Alright. Okay, so let's try a simple example for elastic potential energy. Let's say you have a spring with a spring constant of 500 newtons per meter, and you're going to apply a force and squeeze it, compress it by a distance of, let's say, 10 centimeters. We can calculate the amount of force needed to hold it at 10 centimeter level, at this compression level, right? So you have to start from 0 and you have to keep increasing the force as you go, as you compressing the spring, and at this point where it's shortened by 10 centimeters, there is a certain amount of force you need to apply to hold it there. So that force is given by kx. So I'm not gonna worry about the negative sign here. 500 times 10 centimeters, which is 0.1 meters, so we have 50 Newton meters or 50 joules. This is the force you need. How much work do you have to do? Work you need to do is given by half kx squared equation, half times 500 times 0.1 times 0.1. So we have 50 and then 5 and half of that, 2.5 joules. Let's see. Yeah, looks right, 2.5 joules. So the work you need to do to compress this is 2.5 joules. Okay, then how much potential energy stored in this spring? Potential energy stored or accumulated. The amount of work you do is accumulated or is stored in the spring as energy. So the potential energy in the spring is also 2.5 joules. Now it has the ability to do work worth of 2.5 joules. Okay, so this is how you find elastic potential energy.